In this video, we are going to talk about rational functions. So what a rational function is a polynomial divided by another polynomial. So a rational function is a function that can be written as the quotient or division of two polynomial functions, p of x and q of x. So you have p of x on top here, q of x on the bottom, and the bottom polynomial is required not to be the zero polynomial. All right, so here are some examples of some rational functions, right? A polynomial divided by another polynomial, and same thing on all of these here. Okay, so if you know what a polynomial is, then it's pretty straightforward. Rational function is just the division of two polynomials, and that's it. Okay. The very first thing that we need to do is to find the domain of a rational function. And since rational functions are divisions of two functions, then it's naturally going to have the division by zero problem. And so the domain of a rational function is going to be the set of all real numbers such that the bottom polynomial is not equal to zero. Okay. And so to determine the domain of a rational function, what we would do is just find all real solutions of the equation q of x equals 0. That's the bottom polynomial. So just set the bottom part equal to 0 and solve that out. And the domain is the set of all real numbers except whatever the real solutions of the equation q of x equals 0 are. Okay, so that's really all there is to it. All right, so let's find the domain of this function. F of x equals 2x minus 3 over x squared minus 9x minus 10. That is a rational function, right? And so to find the domain, I'm going to set the bottom part equal to 0. A lot of people will ask, well, what about the top? What do I do with it? And, well, when you're finding the domain, the top doesn't matter, right? Because having 0 on the top part of the fraction in and of itself is not an issue, right? The issue is that when you plug a number in for x and it makes the bottom polynomial equal to 0. Okay, so we take the bottom part of this and set it equal to 0. This is a quadratic equation and it looks like it can factor, right? We would need two numbers that multiply to give us negative 10 and then add up to give us negative 9. So that would be negative 10 and a positive 1, right? Negative 10 times positive 1 is negative 10. Negative 10 plus 1 is negative 9. And since this polynomial has a 1 out in front, then all we need to do is to put those two numbers in, like so. Okay, and so now we have 0 on one side, and the other side is completely factored. So all we would have to do then, right, if you multiply two things and get 0, that means either one of them or the other or both had to be 0. So set each of those factors equal to 0 and solve those out. And you get x equals 10 on this one, and on this one we get x equals minus 1. All right, so the domain just in English would be all real numbers except (10) and negative 1. In interval notation, it would be negative infinity to negative 1, union negative 1 to 10, union 10 to infinity. Okay. All right, and that's really all there is to finding the domain. Just take the bottom part, set it equal to 0, find all the real solutions, and then the domain is all real numbers except those solutions, and that's it. All right, next up are finding the x-intercepts of rational functions. So to find the x-intercepts of a rational function, first you need to know what the domain is. So it's important to find the domain like we just did in the previous problem. And then find the real solutions of p of x equals 0. So p of x, I mean the top part, right, of the rational function, the numerator. Set that equal to 0 and solve. Okay. All right, and we want only the real solutions, right, because complex number solutions don't correspond to x-intercepts. That's something we mentioned in a previous one of the previous videos. All right, next up in step 3, you want to take any real solutions of p of x that are not in the domain of x and get rid of those. Okay, those will not be x-intercepts. And then finally, the x-intercepts are the real solutions of p of x equals 0 that are in the domain of f of x. Okay, so all real solutions of this equation except ones, right, that are not in the domain to begin with. All right, so let's take a look at how we would do that. Okay, it says find the x-intercepts of the function. So number 1, we'll need to find the domain, right, of this and be aware of what the domain is. And basically we just did that in the previous video, right? We know that we would solve x squared minus 9x minus 10 equals 0. So we'd set the bottom equal to 0 and solve that out. And we just did that exact equation, right, in a couple slides ago. And we got x is 10 and negative 1. All right, and so the domain we said was negative infinity to negative 1, union negative 1 to 10, union 10 to infinity. All right, so we found the domain. Okay, so we need to know what the domain is. So now what you would do is set the top part equal to 0 and solve that out. X squared plus x equals 0. Okay, and so we would solve this out. So this is a quadratic again. This one is one of the easier types where the constant term is missing. If the constant term is missing, you can just factor out the x. And that will make this factored. And then we would set each factor equal to 0. So x, set that equal to 0, set the x plus 1 equal to 0. And solve that out. This one's already solved. And here we get 0 and minus 1. Okay. All right. So now what we need to do is to make sure, right, these are both real numbers, right? So that's good. Any complex numbers are not going to be x-intercepts, so we would throw those out. But there aren't any. The next thing we would have to do for the real numbers is to check to see if they are in the domain, right? So is 0 in the domain? Well, yeah, because the domain is all real numbers except minus 1 and 10. So that means 0 is an x-intercept. If they are asking about the ordered pairs, right, or if they want it as an ordered pair, it would be 0, 0. Remember, the y-coordinate of any x-intercept is 0. So and sometimes in the Newton problems, they'll ask for both numbers, right? For the x-intercept, the second number is always 0, right, because it's on the y-axis. All right, the next possibility is negative 1, but we will see, hey, negative 1 is not in the domain, right? Because the domain is all real numbers except negative 1 and 10, so this one has to be thrown out. So there is not an x-intercept at negative 1. The only x-intercept is this one here at 0, 0. Okay. This one is worth looking at the graph. I don't think I've graphed it out here. All right, so let's take a look at the graph on Desmos. Nope. Okay, and so there's what the graph looks like. If we are looking for x-intercepts, let's just double check, make sure that's correct. X squared plus x squared minus 9x minus 10. So you can see there is our x-intercept right there. All right, and if we look at minus 1 to see the situation, right, we can see that there definitely is not an x-intercept there, okay? All right, you can see, so even though -1 was a solution of the top, right, because it was not in the domain of this, it can't be an x-intercept, and you can see, sure enough, right, the graph reflects that. In fact, what is going on there is a tiny little pinhole in the graph right here. That's very, very hard to see, right? If you didn't know that that pinhole was there, then you would just think, you know, the graph looks normal there. But sure enough, there is a tiny little pinhole right here because -1 is not in the domain, right, of that function right here. Okay, so you have to be careful about those. So that's why you need to know the domain ahead of time, right? When you're finding x-intercepts, you have to make sure that these numbers are in the domain. If they are not, right, then they cannot be x-intercepts there. Okay. All right. Next example, or the next topic, is finding y-intercepts of rational functions. That's pretty straightforward. You would just plug in 0 into the function to get the y-intercept, or the y-coordinate of the y-intercept, depending on how you want the answers, as numbers or ordered pairs. Okay, and that works if 0 is in the domain of f of x. It could happen that 0 is not in the domain of x, and if that's the case, then f of x would have no y-intercept. Okay. All right. So find the x-intercept of the function. So I would just plug in 0 and see what I get. All right, on top I get 0 squared, which is 0, plus 0, which is 0. On the bottom I get 0 squared minus 9 times 0 minus 10. That's going to come out to be 0 over -10. All right, and so 0 divided by any non-zero number is just 0. So the y-intercept, right, will be 0. Or if we are looking for the ordered pair, the x-coordinate, right, of a y-intercept will always be 0 because it's on the y-axis. So the answer will be 0 if they're just looking for the number, or if they're looking for the pair, it will be 0, 0 in this case. And here you can see, if I zoom back out, you can see right there that x-intercept is also a y-intercept on this one. Okay. All right. The last topic that we're going to talk about for rational functions are horizontal asymptotes. There are also some other topics that we won't be talking about in this class, but also are fairly important, like vertical asymptotes. We still have a lot to cover, so we're just kind of going to move on to the next topic here. And in the Newton homework, only these horizontal asymptotes are covered. So a horizontal asymptote of a graph is a horizontal line, and every horizontal line has this format: y equals a number. where the graph approaches the line as the inputs increase or decrease without bound. All right, so it's what happens if, so a line is a horizontal asymptote, and I usually will draw those in as a dotted line. If as the graph goes really far to the right, right, as we go really far to the right, the graph of the function gets closer and closer to this horizontal line. So it flattens out as you go farther to the right, or it could also be farther to the left. So it could be either of those or also both as well. Okay. All right, so let's take a look. So here's an example of a function. Here's its graph. And this graph has two horizontal asymptotes, y equals 2, which is this upper one right here, this upper dashed line. You can see that the graph of this function, right, gets closer and closer to the graph of this horizontal line the farther you go there. You can see that little arrow indicates that the graph just keeps doing that same behavior as you go far to the right. All right. And over here, y equals minus 2 is also a horizontal asymptote, right, of this function here. So as I go really far to the left, you can see that the graph is getting closer and closer to this line right here at y equals minus 2. Right, so y equals minus 2 is the equation of that dashed line. The graph's getting closer and closer to that. All right, so a function can have at most two horizontal asymptotes here. All right. However, right, for rational functions, a rational function can only have either 0 or 1 horizontal asymptote. So this graph that I showed you here before, right, is not a the graph of a rational function. Okay, so a rational function has either 0 or 1 horizontal asymptote. So let's take a look. All right. So this function, f of x equals x squared over x minus 3, it's a rational function. It has no horizontal asymptotes. Right here, the graph, as we go really far off to the right, the graph just keeps going up and up like this, right? And so it does not, the graph does not flatten out, right, to look more and more like a horizontal line. Same thing here, right? As we go really far to the left, you can see the graph just keeps going down like this. And the graph and this arrow indicates it just keeps with that same behavior there, right? So the graph here is not flattening out and getting closer and closer to a horizontal line. So this is an example of a rational function with no horizontal asymptotes. It does have what's called a slant asymptote, which is an asymptote, right, that is not horizontal or vertical. It does have a vertical asymptote right in here as well. But in this part, we're really only talking about horizontal asymptotes. So we won't talk about the slant ones or the horizontal ones. All right, this function, 3x minus 1 over x plus 2, has one horizontal asymptote, y equals 3. And so y equals 3, you can see I drew it in here with the dotted line. Dotted line to indicate, it's not really part of the graph, but just to illustrate that there's an asymptote there. It's just a lot easier to see if I put that dashed line in there. And so we can see that the graph of this function is getting closer and closer to this horizontal line right here. So it's getting flatter and flatter, and will continue, right, to get closer and closer to this horizontal line like that. Same thing over here, right? The graph's just going to continue to flatten out and get closer and closer to where this dotted line is. All right, so that's the situation. It's either 0 horizontal asymptotes or 1 horizontal asymptote for a rational function. All right, I just repeated that slide there. Forgot to take those out. Okay, so now what we want to be able to do is to look at or determine the horizontal asymptotes of a rational function, basically just by looking at the graph, okay? Or looking at, not at the graph. At the graph, it's pretty straightforward, right? But we want to just be able to look at the function itself, right, and determine what the situation is with the horizontal asymptotes. Okay, so here I have a rational function, And instead of just putting p of x over q of x, I've kind of spelled all this out here. Here, this top polynomial is written in descending powers of x. Okay, the degree of the top, right, is m. That's, remember, the degree is the highest power. All right, and on the bottom, right, the degree is n. Okay, that's the highest power of x. All right, so, and the leading coefficient on the top is a sub m. The leading coefficient on the bottom is b sub n. Okay, so those are just numbers, right? The numbers that are out in front of the highest power. All right, so if you remember when we talked about end behavior of a polynomial function, right? With the end behavior of a polynomial, remember what I said was that it's completely controlled by the leading term. Okay, so this polynomial's behavior as you go really far to the right or really far to the left is controlled by the leading term. And this one is also a polynomial, right? And so its behavior as you go really far to the right or really far to the left, right, is controlled by this leading term again. So if you watch the video about end behavior of polynomial functions, right, we talked a little bit about why that's so, and that these powers, because they are bigger than all of the other powers, dominate. These numbers are going to be really big when x is really, really big or really, really small. In other words, when you go really far to the right or really far to the left. So the asymptotes, right, of a function are going to occur of a rational function, right, are going to occur when you go really far to the right or really far to the left, right? So it only makes sense that the situation with the asymptotes is completely controlled by the two leading terms, right, of this thing. So all we really have to do to determine, right, horizontal asymptotes is to look at these leading terms right here. Okay, so the first thing that we are going to look at is the degree, right? We're going to look at the degree of the top polynomial, which is m, and the degree of the bottom polynomial, which is n. Okay, so those are going to be two numbers, right? And so two numbers, there's basically three possibilities about which one is bigger, right? So here, right, if the top one is less than the bottom, right, the top and the bottom could be equal, right? And the top could be bigger than the bottom degree, okay? And so that's going to determine the situation. All right, and so it's basically where is the bigger power? Is the bigger power in the top or the bigger power in the bottom? So if the bigger power is in the bottom, right, then will have one horizontal asymptote. That horizontal asymptote will be y equals 0. The bottom is if the bottom is the bigger power, it basically drives everything to 0, right? If you take a number on top and divide by a number that gets bigger and bigger and bigger, the result will go to 0. Okay. The second case is when the powers are equal, right? If the degree of the top and the degree of the bottom are equal to one another, well, then that's going to have one horizontal asymptote. The horizontal asymptote is going to be the ratio of the leading coefficients. So that should be m right here. Sorry, typo. The leading coefficient on the top is a sub m. The leading coefficient on the bottom is b sub n. Okay, so whatever this number is with the highest power of x on top over this number, which is the highest power of x on the bottom. So here the powers are the same, so they kind of cancel each other out, and you get a number as the answer. The number that you get is the ratio or division, right, of the leading coefficients. And then the last case is that the bigger power is in the top. If the bigger power is in the top, then that makes this top part bigger than the bottom part, right, in the long run when you go really far to the right or really far to the left. And that will mean that f of x will have no horizontal asymptote in that case. Okay. So it really is pretty straightforward to determine the situation. You just have to remember these three cases. All right, let's look at an example of each of those. All right. On this first one, it says find the horizontal asymptote of the rational function if it has one. Okay. All right, so looking at the degree of the top, right, the highest power of x, right, is 1 on top. So the top is a degree 1. The bottom is a degree 1, right? So the powers are the same in the top and the bottom. That means that this rational function will have a horizontal asymptote, right? So it'll be y equals, and it will be the ratio of the leading coefficients. So it'll be 3 halves, like that, okay? So this has one horizontal asymptote, y equals 3 halves. All right, let's take a look at the graph, and you can see the graph here. 3 halves is about 1.5, right, which is right here. And if you graph it out, sure enough, right, the graph is getting closer and closer to y equals 3 halves as you go really far to the right or really far to the left. Now, the horizontal asymptotes don't have any effect in the middle, okay? It's just what happens as you go really far to the right or really far to the left. All right, next example I have, find the horizontal asymptote of the rational function if it has one. All right, so I need to look at the degrees of the top. The degree of the top is 1. The degree of the bottom is 2. All right, remember that's the highest power of x. On top is 1, highest power of x on the bottom is 2. The degree of the bottom is bigger than the degree of the top, so this function will have a horizontal asymptote. It will be y equals 0, okay, which is the x-axis, and that's it. All right, so f of x has one horizontal asymptote, y equals 0, and here it is. You can see that's what the graph of this looks like, and you can see that it gets closer to, the graph gets closer and closer to the x-axis as we go really far to the right or really far to the left. All right, last example, it says find the horizontal asymptote of the rational function if it has one. The degree of the top is 3. The degree of the bottom is 1. All right, and so therefore this rational function will have no horizontal asymptotes. Okay, and you can see if you graph it out, you go really far to the right, looks like this. Right, goes up really fast. You go really far to the left, right? The graph also goes up like this as well. Okay. So that's pretty much it. You look at degrees, the degree of the top and bottom polynomial to figure out what the case is, right? And then you just have to know the results of, or the outcome of each case. All right, so that is it on this section on rational functions. Like I mentioned, there are some other topics we will not discuss at the moment, but maybe later on. Okay, so do these problems, the asymptotic behavior of rational functions, student assignment, and the graph and applications of rational functions, student assignment.